In this presentation, I'm going to explain buck-boost converter, the working of buck-boost converter, the design of the inductance and the capacitance, and a design based on this calculation of inductance and capacitance. And also, I'll be explaining the closed loop working of a buck-boost converter. Now coming to the buck-boost converter. Buck-boost converter can also be called as a step-down and step-up converter. Step-down up converter. It can either the voltage can be step-down or voltage can be step-up. That's why it's called step-down up converter or buck-boost converter. Actually, basically, it can be considered as a two converters. They are connected in cascade. For example, the input is given to a buck converter, and the output of the buck converter is given to a boost converter. Therefore, the total transfer function will be the product of course, the product of these two things. That is d into 1 by 1 minus d, or d by 1 minus d. That is the total gain as such. Therefore, output divided by input will be d divided by 1 minus d. Therefore, in buck-boost converter can be obtained by cascade connection of a step-down as well as step-up converter. They are connected in cascade. In steady state, output voltage conversion ratio, that voltage conversion ratio will be the product of this conversion ratio of each one. That is d into 1 by 1 minus d. The product of the conversion ratio of the two converters in cascade. Therefore, that is why the V0 by Vd will become now d by 1 minus d. Therefore, a buck-boost converter provides an output voltage less than or greater than the input voltage. Therefore, it can provide either the output voltage more than the input voltage or less than the input voltage, or it can be either boosting action or bucking action is possible. One other problem or one other point to be noted is that output voltage polarity is opposed to that of the input voltage. Here plus and minus, but the output voltage is here plus and minus. So the voltage are opposite polarity. Output and input polarity are opposite. And therefore here the same buck-boost converter or a step-down, step-up converter can be realized rather than connecting two buck and boost in cascade. It can be realized by a single circuit like this one. That is, this is a circuit topology of a buck-boost converter in which the input voltage source Vd, and there is a MOSFET switch is there, and this is an inductor is there, and this is a diode, and this is a capacitor that is connected across the load. The output voltage is measured here plus and here minus, and we'll be going to the details of this topology, buck-boost converter topology. Now coming to the buck-boost converter in continuous conduction mode, in CCM, it's called continuous conduction mode. As the continuous conduction mode means that the current through the inductor never goes to zero. Always the current through the inductor will be more than zero. That is why continuous conduction mode. And here, this is the circuit topology as I already explained in the previous slide. Here, of course, there are two cases comes. When switch is on, what is the equivalent circuit? When switch is off, what is the equivalent circuit? And what is the relation between the inductor voltage in each case? Therefore, for example, first here, when the switch is on here, when switch is on, the equivalent circuit is this one. That is, the input voltage Vd will be coming across the across the inductor. Diode does not conduct, because that's a reverse bias. Diode does not conduct, or this will be open circuited. Therefore, this is the equivalent circuit of this buck-boost converter when switch is S is on here. Therefore, the voltage, the Vd, the input voltage is coming across the inductor, and the output current is being supplied by this capacitor. Of course, what we are assuming that always the current through the load is a constant. Therefore, a constant current is flowing through the load here, and that is being supplied by this capacitor. Therefore, this is the equivalent circuit when switch is on here. And in that case, the voltage across the inductor is same as the input voltage Vd, or that is a plus Vd. And since the voltage is positive here, as you know, that one VL equal to L di by dt. Since voltage across the inductor VL is positive, DIL by dt will be positive. That is why the current through the inductor is having a positive slope, or that is increasing linearly. And once the switch is off here, that is when switch is off here, then the corresponding equivalent circuit is this one. This is off here. Then this is the equivalent circuit. Therefore, the energy stored in the inductor will be supplying required power for the load as such. And in this case, this is the equivalent circuit. And if you apply the Kirchhoff's voltage law, we can get that one this is the voltage across the inductor, that is VL, and plus the output voltage V0 equal to 0, or the voltage across the inductor equal to minus V0. Therefore, when the switch is off, the voltage across the inductor equal to minus V0 or minus of the output voltage. Here we are measuring the output voltage plus here and minus here. And since the voltage across the inductor is equal to minus, here the current through the through the inductor is having a negative slope, because DIL by dt is equal to negative, since the voltage across the inductor equal to negative. Therefore, this is the current through the inductor, and this is the voltage across the inductor over one switching period, and this is the equivalent circuit corresponding to the on position of the switch S, and this is the equivalent circuit corresponding to the off position of the switch. Now continuing the buck-boost converter in mode 1, as I already told here, when switch is on, we consider it as a mode 1. When switch is on, this is the equivalent circuit, and the voltage across the inductor is same as the input voltage Vd here. That is why the voltage across the inductor equal to Vd, and since the voltage is positive, the current is through the inductor is building up. From it is marked as from I1 to I2. The current is increasing from I1 to I2, and of course the current through the capacitor, because the load current is assumed to be constant. That is why that is to be supplied by the capacitor. The capacitor is of course discharging a constant current that is going through the load as such. So the capacitor current is given by minus I0, because minus I0 is the capacitor current, and voltage across the inductor equal to plus Vd, and the current through the inductor is having a positive slope, because VL equal to LdI by dt. Since the voltage is positive, DIL by dt is positive. Therefore, the current is building up from I1 to I2, and the load current is assumed to be constant. And when the switch S is turned on, the diode D is reverse bias, because here when it is turned on, the diode is getting reverse bias. Now this is an equivalent circuit, reverse bias, and current flows through the filter inductance L. This is the filter inductance L, and the current through the inductor increases from I1 to I2. From I1 to I2, the current decreases linearly. It increases, and the voltage across the inductor is same as the input voltage Vd, and the filter capacitance C keeps the voltage across the load, which is equal to V0, or Vc is equal to the voltage across the capacitor is same as the load voltage V0, and current through the capacitor is a constant current of minus I0 is flowing. Therefore, these are the parameters like voltage across the inductor, current through the inductor, current through the capacitor, as well as the load current for when the switch is on, that is in mode 1. Now buck converter in mode 2, that is switch is off. When switch is off here, the corresponding equivalent circuit is this one. Therefore, here the inductor, filter inductor, and capacitor come across the load here, and again the voltage polarity is here plus and here minus. It is opposite to the input voltage, plus here and minus here. And here, since the voltage across, if you apply the Kirchhoff's voltage law here, we'll be getting voltage here plus minus VL plus V0 equal to 0, or VL equal to minus V0, or the voltage across the inductor equal to minus V0. Therefore, since the voltage across the inductor equal to minus V0, the current through the inductor equal to having a negative slope from, that is VL equal to LdI by dt. Since VL is negative, DIL by dt is negative, the current is having a negative slope, that is changing from I2 to I1. And here, since we are assuming a constant load current I0 here, then the current through the capacitor is given by whatever this current minus this one. That is, here the IL minus I0 is the IC. Therefore, here IL is this one, and I0 load current is this one. IL minus I0 equal to IC during that when switch is off here. That is why here we'll be getting I2 minus I0, and that is dropping to until I1 minus I0. Therefore, this is the current through the capacitor when the switch is off, and this is the voltage across the inductor, which is equal to minus V0, and this is the current through the inductor, which is changing from I2 to I1, and this is the load current, which is assumed to be constant. Therefore, the voltage across the inductor equal to minus V0, and D conducts, and the voltage across the inductor equal to minus V0, and current through the inductor decreases from I2 to I1 linearly, and since VL equal to V0, VL equal to minus V0, since this is equal to minus V0, here we will be getting it is equal to minus V0, means here minus and here plus here, and here diode is forward bias, that is why diode is conducting. This is the equivalent circuit, and the load current I0 is assumed to be constant. What we are assuming is that the current through the load is constant, which is equal to I0 or I0. And capacitor current, as the capacitor current is given by, which is equal to the inductor current minus the load current. Therefore, that is why the capacitor current is changing from I2 minus I0 to I1 minus I0. That is from I2 minus I0 to I1 minus I0. That's the current through the capacitor. And during off period, of course, IC equal to IL minus I0. That is why I2 minus I0 to I1 minus I0. Now let us see the inductor voltage and volt second balance of a buck boost converter. Basically, as we have seen, when switch is on, the voltage across the inductor equal to VD, and when switch is off, the voltage across the inductor equal to minus V0. This is since the voltage across the inductor equal to plus VD during on period, the current through the inductor is having a positive slope, that is changing from I1 to I2. And when the switch is off here, the voltage across the inductor will become negative, which is equal to minus V0. And that is why the current through the inductor is having a negative slope, that is changing from I2 to I1. Therefore, this is the current through the inductor and this is the voltage across the inductor. The basic relation voltage across the inductor is given by L into DIL by dt. And during the on period, the voltage across the inductor equal to VD, or VD equal to L DIL by dt, or the rate at which the current is building up is given by DIL by dt equal to the input voltage VD divided by the inductance value VD by L. And during the off period, the voltage across the inductor equal to minus V0. Therefore, minus V0 equal to L DIL by dt, or DIL by dt is equal to minus V0 divided by L. Therefore, this is the rate of change of current through the inductor when switch is off, and this is the rate of change of current through the inductor when switch is on. And in any switching converters under steady state condition, the net change in inductor current over one switching period must be 0, meaning that this current, that is the inductor current at 0 time to 0, should be same as inductor current at time Ts. Therefore, this current is same as this current. Otherwise, that is in steady state, initial and final value of the inductor current are equal. This current is same as this current, or we can say that IL at Ts is equal to IL at 0. Inductor current at time 0 equal to IL at Ts. Otherwise, what happens is that if there is a, if there's not the here, then the here net flux increases, or flux will be causing the net flux will be developed, and finally the core gets saturated. Therefore, that we'll see that volt second balance concept as such. Therefore, here the voltage across the inductor when switch is on, that is equal to say VD here, and when switch is off here, it is equal to minus V0, and we'll be seeing that the net area should be equal to 0. Otherwise, that is volt second concept, that is product of voltage and time, that net area should be equal to 0. Otherwise, net flux will be developing and the core gets saturated. In order to obey this one, the condition is that the current at 0 should be equal to the current at Ts. We'll see that. Therefore, and again, if you coming to the basic equation, VLT equal to A L DIL by dt here, or the current through the inductance at Ts. Here, this is equal to what is the current at the 0, that is this one, plus what the, due to this change in current, what is the corresponding change, that is 1 by L integral 0 to Ts VLT dt. Therefore, if you substitute here IL Ts minus IL 0 equal to 1 by L integral 0 to Ts VLT dt, or since this initial value of the current is same as of Ts here, this current, since this is equal to 0, 1 by L integral 0 to Ts VLT dt should be equal to 0, or integral 0 to Ts VLT dt should be equal to 0. That is voltage and time, the product, that is nothing but the area. Therefore, the average voltage across the inductor over one switching period should be equal to 0, means that this positive area should be equal to negative area. The net area over one switching period should be equal to 0. Otherwise, as I already explained that one, the net flux or the change in flux occurs, and after a few cycles, the flux increases and the core gets saturated. Therefore, in order to avoid that one, the average voltage across the inductor over one switching period should be equal to 0. This is called volt second balance concept, that is derived from constant flux theorem. Now, continuing the volt second balance concept of buck boost converter. Thus, under steady state operation, the integral of the inductor voltage over one switching period must be equal to 0. That is, integral 0 to Ts VLT dt should be equal to 0, meaning that this positive area, this is the voltage across the inductor, this positive area should be equal to the negative area. After one switching period, the net area should be equal to 0. Because as I already told you, the product of voltage and time, that is nothing but, of course, the flux linkage, or the change in flux or change in flux linkage, that should be 0 after one switching period. The above equation says that the total area or the volt second, the under VLT waveform must be equal to 0. Positive area should be equal to negative area. Therefore, that is a condition to be satisfied. Volt second balance concept as such. It is called, if you substitute this area here, it is equal to, this is a VD and this time is equal to on period. VD into T on plus this is equal to minus V naught into this time period equal to TS minus T on. TS minus T on, that should be equal to 0. Again, VD into T on minus V0 into Ts plus V0 into T on should be equal to 0, or V0 into Ts minus T on equal to VD into T on, or that indicates that V0 by VD equal to on period T on divided by Ts minus T on. For dividing the Ts numerator and denominator, we will be getting V0 by VD equal to T on by Ts divided by 1 minus T on by Ts, or which is equal to T on by Ts equal to the duty cycle D. Therefore, that is equal to D divided by 1 minus D. Therefore, this is the equation between, relation between output voltage, average output voltage and input voltage. V0 divided by VD should be equal to D by 1 minus D, where D is called the duty cycle, which is equal to the on period divided by the total time period, TS. Therefore, the voltage conversion ratio V0 by VD equal to D by 1 minus D, where D is called the duty cycle, T on divided by TS. TS is the time period. T on is the on time period, on period divided by total time period, TS. And here the volt second balance means that here integral 0 to Ts VLT dt, that can be written as integral 0 to T on VLT dt plus integral T on to Ts VLT dt. Therefore, this is representing this one positive area. The second quantity represents the negative area. Therefore, the total volts again, that is the integral Ts VLT, that should be equal to 0, means that this sum of this area, positive area plus negative area, should be equal to 0, or this positive area should be equal to the negative area. The total area should be equal to 0. That is the volt second balance concept of of course, any converter. Now, continuing the volt second balance of a buck boost converter, and here we are seeing the the ratio, the V0 by VD, that conversion ratio equal to D by 1 minus D. Now, the D can be, if the value of the D is less than 0.5, output voltage will be less than the input voltage. So, if D is less than 0.5, the output voltage is less than input voltage, or that bucking operation is taking place. Now, if the duty cycle value is more than 0.5, then we can, the V0 by VD will become, it is more than 1, or V0 equal to more than 1 of the VD, or that's a boosting action is taking place. Or if duty cycle D is more than 0.5, output voltage is more than the input voltage, or boosting operation is taking place. Therefore, if D is less than 0.5, bucking operation is taking place. If D is more than 0.5, boosting operation is taking place. Therefore, in continuous conduction mode, neglecting the power loss associated with that one. For example, here, bucking and boosting, we can see that one. For example, if say, if C equal, D equal to 0.2, assume that D equal to 0.2. For the 0.2 divided by 1 minus 0.2. For 0.2 divided by 0.8, or 2 by 8, or 1 by 4. For V0 equal to 0.25 times VD. That is, if D equal to less than 0.5. Another thing, if D is more than 0.5, assume it is equal to 0.8. D equal to 0.8. Therefore, it is V0 by VD equal to 0.8 divided by 1 minus 0.8, or 0.8 divided by 0.2, or 8 by 2, or it's equal to 4. Therefore, output voltage equal to 4 times the input voltage. That's called the boosting action. Therefore, depending upon the value of the duty ratio, if it is less than 0.5, it is a bucking operation. If it is more than 0.5, it is the boosting operation. Now, again, in continuous conduction mode, neglecting the power loss associated with all the circuit elements, the input power can be equal to the output power. Now, whatever the input power is equal to the output power means that input voltage is VD and average input current equal to ID. VD into ID equal to average output voltage equal to V0, average output current equal to I0, therefore V0 into I0. Assuming that all these are ideal, there is no loss for the inductor, capacitor like diode, or even the switch. In that case, we can get V0 I0 equal to VD into ID, or V0 divided by VD equal to ID by I0. Therefore, in that one we can say that V0 I0 is the average output current and ID is the average input current. V0 is the average output voltage. Now the basic conversion ratio is V0 by VD equal to D by 1 minus D, and I0 by ID equal to 1 minus D divided by D. Therefore, where D is the duty cycle, or which is equal to on period divided by the time period, or T on divided by Ts. Now let us see the design of the inductance value of buck boost converter. Design of inductance L and the capacitance C. Therefore, this is the current through the inductor and this is the voltage across the inductor. And the change in inductor current is represented that this is equal to I1, and here it is represented that this is equal to I1, and this is I1 and this is I2. This is I1 and this is I2. Same thing shown here. Current is changing from I1 to I2 when switch is on, and when switch is off, this is again coming back to I1 from I2 to I1. Therefore, the change in current is given by delta IL, which is equal to the same here also, delta IL, which is equal to I2 minus I1. Delta IL is given. This change in current is because of the positive voltage VD through a period of T on. For the rate at which the current is building up is given by, because VL equal to LdI by dt, or di by dt equal to VL divided by L. In this case, VL equal to VD. Therefore, VD divided by L is the rate at which the current is building up. Therefore, VD by L, and for a period of on period T on, therefore into T on. Therefore, this is the change in current I2 minus I1, or delta IL is given by VD by L into T on. Substituting for T on, which is equal to DTS, for VD into DTS divided by L, or dVD divided by Ts equal to 1 by Fs. Therefore, dVD divided by Fs into L, where Fs is the switching frequency, D is the duty cycle, Vd is the input voltage, L is the inductance. Therefore, the change in inductor current equal to dVd divided by Fs into L, or from this equation you can find out what is the inductance, which is equal to dVd divided by Fs into delta IL. So this is the value of the inductance to be connected. Now to bring the inductor current ripple to delta IL. That is the way in which the L can be designed. Now let us see the design of capacitor as such. Capacitor, to design, we have to see what is the change in voltage as such. For when you are designing an inductor, we'll see the ripple current. When you are designing a capacitor, ripple voltage. And the ripple voltage means that here the capacitor is current, and when switch is on here, the load current is being supplied by the capacitor. Therefore, the load current is constant. Therefore, the capacitor current equal to minus I0. Therefore, of the magnitude of current equal to I0. Okay, of course. Therefore, because of a constant current of I0 to the capacitor voltage is of course discharging here. Capacitor is discharging. The capacitor voltage is changing from this voltage value Vc on, that is changing by delta Vc, or Vc minus delta Vc, or the change in voltage equal to delta Vc because of the constant load current I0. Therefore, the change in capacitor voltage delta Vc is because of the constant discharge current I0 from the capacitor for a duration of on period. That is the reason why the capacitor voltage is changing delta Vc, because of a constant current of discharge. Therefore, delta Vc equal to, that is this voltage Vc0 minus Vc on period. That is the change in voltage, capacitor voltage, which is equal to 1 by C integral 0 to T on. The current equal to IC dt, or IC can be calculated as V0. Therefore, 1 by C or delta Vc equal to 1 by C integral 0 to T on I0 dt, or here substituting that one I0 into, or the constant load current I0 or I0, I0 into T on divided by C, or I0 into T on equal to D times Ts divided by C, or 1 by Ts equal, or Fs equal to 1 by Ts, or here substituting that one here, D into I0 divided by Fs into C. D is the duty cycle, I0 is the load current, Fs is the switching frequency, and C is the capacitance. Therefore, the capacitance value can be calculated, or C equal to D I0 divided by Fs into delta Vc. Therefore, this is the way how we can calculate the value of the capacitance, required value of the capacitance based on the voltage ripple, allowable voltage ripple of the capacitor delta Vc. Based on that, you can calculate what is the value of the capacitance. Similarly, to calculate the inductance, how much permitted value of the ripple current through the inductor. Based on that, you can design L and S. This is the way in which you can design the inductance as well as capacitance of a buck boost converter. Now let us see a problem based on this buck boost converter problem. A buck boost converter has an input voltage of 12 volts and the duty ratio D equal to 0.25 and the switching frequency is 25 kilohertz. The average load current equal to 1.25 amperes if the inductance L equal to 150 microhenry and the capacitance equal to 220 microfarad. Determine the average output voltage, ripple current of the inductance or delta IL and delta VC, that ripple voltage of the filter capacitor. These are the questions. First, let us see the, of course, the average output voltage. Duty cycle is given as 0.25. The input voltage is given as 12 volt and duty cycle is given as 0.25. And this is the, buck boost converter circuit as we already seen here. And the switching frequency is given as 25 kilohertz. And the average load current is given as 1.25 amperes. Inductance value 150 microhenry and C equal to 220 microfarad. Therefore, the equation V0 by Vd equal to D by 1 minus D. The average output voltage divided by input voltage equal to D by 1 minus D, and where the duty cycle is given as 0.25. And substituting that one, we can get V0 equal to D by 1 minus D into the input voltage, or 0.25 divided by 1 minus 0.25 into 12 or 4 volt. Of course, polarity will be plus here and minus here because here the polarity plus, let's say polarity wise inversion is there, but the magnitude equal to 4 volt. Then next, the average output voltage we have to find, that is equal to 4 volts. Second, ripple current of the inductor. Ripple current of the inductor, already we have seen the equation. Delta IL is equal to dVd divided by Fs into L. Duty cycle equal to 0.25. Input voltage equal to 12. The switching frequency equal to 25 kilohertz. And the inductance value is given as 150 microhenry. Substituting that one, will be getting 0.8 amperes. Therefore, the ripple current through the inductor is given by 0.8 amperes. Third case, the ripple voltage of the filter capacitor. The ripple voltage delta Vc equal to d I0 divided by Fs into C. D equal to 0.25, I0 1.25 amperes, Fs equal to 25 kilohertz, and 220, it is equal to microfarad, 220 into 10 raised to minus 6, or it is equal to 56.8 millivolt. Therefore, this is the ripple voltage across the capacitor. This is the ripple current through the inductor or delta IL, and the average output voltage magnitude equal to 4 volt. The polarity here plus and here minus. Now let us the closed loop control of buck boost converter. That is, this is a simulating model, and here there's a input voltage is given. It's equal to 12 volt, and this is 6 volt. It is a buck boost converter, like this is a switch as and this is a diode, inductor, capacitor, load is there, and output voltage is sensed, that is compared with the reference, and the error is given to a PI controller, and the PI controller is compared with a sawtooth waveform, and the output of that comparator, that is given as an input signal to the switch. Therefore, this is the basic method of controlling using a PI controller of a buck boost converter, a closed loop control of a buck boost converter. Continuing the closed loop control of buck boost converter, in which we have seen an input voltage perturbation is done. Input voltage is suddenly changing from say 20 volt to 40 volts. Up until this one, 20 volt is there, and then again it is changing to 40 volts. But the reference voltage we kept it as 30 volts. The output voltage what we want is the 30 volt. Whether it is input is 20 or 40, we want to get a constant output voltage of 30 volts. Therefore, when input is equal to 20 volts and the reference voltage equal to 30 here, output is again 30 volts. But in this case, the output is 30 and input is equal to 20. That is why boost operation is taking place. During this period, the circuit is working as a boost converter. And from this portion, that is from the input voltage is doing a perturbation from 20 volts to 40 volts. Still, the reference voltage what we kept is 30 volts. Therefore, we want to get a constant 30 volts here. Of course, there is a spike is there that during the transition, and during this operation, input voltage is equal to 40, but you want to keep the output voltage equal to 30. Therefore, it is the 42 input voltage, output equal to 30. Therefore, a bucking operation is required, or that is working as a buck converter. Or this bucking operation is taking place during this. That is when input voltage is more 40 volts, and when input voltage equal to 20, it is the boosting operation is taking place. Therefore, the circuit is working as either boost converter or a buck converter depending upon the input voltage, because reference voltage we kept as a 30 volts. We want to get output voltage 30 volts independent of the input voltage perturbation or variation.